In today's assignment, we are going to look at optoelectronic devices. So, this is assignment 8. In assignment 7, we looked at problems dealing with general interaction of light with semiconductors. Today, we are going to look specifically at some problems leading to devices. So, in the classes, we looked at photodetectors, solar cells, LEDs and lasers. We did a bit of solar cell trying to calculate the current voltage characteristics. So, some of the assignment problems here will mostly deal with solar cells. We will also look a bit at photoconductors and also a problem on LED. We will not be focusing on lasers, because the way the laser works is very similar to how an LED works, except that you have a population inversion that is created and you have an incoming photon that stimulates the emission. So, let us go to problem number 1. In problem 1, we have a PIN diode. So, you have a P type, intrinsic and an N type. So, we are asked to draw a qualitative energy band diagram both in equilibrium, forward and reverse bias. So, we have a PIN diode. So, we have essentially two interfaces, one between the P type and the intrinsic material, the other between the intrinsic and the N type. For simplicity, we will just take this to be a homo junction. So, all the three materials are the same. The only difference is in the doping concentration and the type. So, I will start with the P, I and N. So, we can draw the energy band diagram for all three of this. So, the material is the same. So, the valence band and the conduction band are essentially located at the same point. In the case of a P type material, the Fermi level is close to the valence band. For an intrinsic, it is close to the middle, and for an N type, EF is close to the conduction band. So, when we have this in equilibrium, we know that the Fermi levels must line up. So, in equilibrium, I have the Fermi levels line up. Far away from the interface, your material still behaves as the same. So, this is P type, this is intrinsic, and this is N type, and making sure that the band gaps are approximately the same, and then we can join all three. So, essentially this is your PIN junction in equilibrium. There are two contact potentials that are developed, one between the P and the intrinsic region and one between the intrinsic and the N type region. So, we can again draw this in both forward and reverse biased. In the case of a forward bias, the P is connected to positive and N is connected to negative. So, that carriers are injected into the device and the barriers are lower. In reverse bias, it is the other way round, P is connected to negative, N is connected to positive, so that the barriers actually increase. So, let me draw that next. So, in the case of a forward bias, P is connected to positive and N is connected to negative. So, on this side I have a P type semiconductor. At the center I have an intrinsic, and here I have an N type. If you draw this slightly more clearly, so the important point is that in the case of a forward bias, the barrier is lowered so that you can have a current going through the device. Now you have a reverse bias. So, P is connected to negative and N is connected to positive. So, here the barrier is actually increased. So that now it has become more difficult for the current to flow through. So the last part of the question asks, for use as a photo detector, do we use the PIN junction in forward or reverse bias? So if you look at the working of a photo detector is one where light falls onto your material, so onto your device, and essentially this creates electron and holes which are detected as a current, and the intensity or the value of the current is directly proportional to the intensity of the light. So for this to happen, we essentially want the current through the device to be very small, because if there is a background current, that will essentially act as noise to the current that is generated by light shining on the material. So this happens when the PIN junction is essentially connected in reverse bias, so that electrons and holes that are typically created in the intrinsic region get separated. So if I have a P, I and N, and I have light shining onto the material, electron is generated here, a hole is generated here. These electrons move to the N side and the holes move to the P side because of reverse bias, and this gets detected as a current. The current once again is proportional to the number of electrons and holes that are generated, which is directly proportional to the intensity of the light that is falling. So for use as a photo detector, the PIN junction or the PIN diode must be connected in reverse bias. So, let us now go to problem 2. So, problem 2 essentially deals with an LED. LED is your light emitting diode, that based upon the fact that you inject electrons and holes into your material. A typical diode is nothing but a p-n junction. These electrons and holes recombine and basically give you light. The wavelength of the light depends upon the band gap of the material. So, by tuning the band gap of the material by adding different dopants can essentially tune the light output. So, in this particular case we are asked to show that the change in the emitted wavelength lambda, so d lambda over dt. So, the change in wavelength with respect to temperature is approximately given to be minus hc over Eg square dEg over dt, and then we are asked to do the calculation for a gallium arsenide system where the band gap is given and also the temperature variation is given. So, the first part can actually be very easily shown. So, I just described the working of an LED and said that the wavelength of the light is approximately equal to the band, depends upon the band gap of the material. So, lambda, which is the wavelength of the light, is equal to hc over E, where E is the energy of the photon. This in turn depends upon the energy of the electron and hole that are involved in recombination. This electron and hole is usually very close to the valence band edge and the conduction band edge. So, that this can be written approximately as hc divided by Eg. So, usually the electron or the hole is not located exactly at the band edge, where there is some thermal energy which is typically of the order of kT, but we can ignore the thermal energy and say that lambda is approximately hc over Eg. If you look at this expression, h and c are essentially constants, the only variable is Eg. So, if we differentiate this, we get d lambda over dt is nothing but minus hc over Eg square, since you are differentiating 1 over Eg times dEg by dt. So, we are asked to do this calculation for gallium arsenide. Gallium arsenide has an Eg of 1.42 electron volts. This typically lies in the infrared region, and the value of dEg or dt is also given, 4.5 times 10 to the minus 4 electron volts per Kelvin. So, we can calculate the change in wavelength with respect to temperature. So, d lambda over dt hc square over Eg times dEg over dt. So, we can substitute all the values and this gives you a value 0.277 nanometer per Kelvin. So, if you look at it, dEg over dt with respect to temperature is negative, which means the band gap essentially decreases with rise in temperature. Corresponding to a decrease in band gap, the wavelength will increase because lambda is inversely proportional to energy. So, d lambda with respect to temperature is a positive quantity. So, the question also says your delta T is nothing but 10 degrees. So, in Kelvin this is the same 10 Kelvin. So, the corresponding change in the wavelength delta lambda is nothing but 2.77 nanometers. So, all we are doing is substituting delta t here and then just multiplying. So, let us now go to problem 3. So, problem 3 relates to a solar cell. So, we have a solar cell at room temperature and it is under illumination. So, the intensity of the light is given. So, I is 500 watts per meter square. The short circuit current is also given. So, ISC is 150 milliamps and also the open circuit voltage VOC is 0.53 volts. So, the question asks what is the short circuit current and also the open circuit voltage when we double the value of the illumination. So, illumination goes from 500 to 1000 watt or 1 kilowatt per meter square. Similarly, what are the values when the illumination is essentially halved? So, the short circuit current is essentially the current when this voltage is equal to 0 and ISC is proportional to the intensity of the light that is falling. So, typically it is equal to some constant times IPH. So, IPH, let me write the subscript here. IPH is nothing but the intensity of the photons that is falling onto your solar cell. So, ISC is essentially some constant k times IPH. VOC, which is your open circuit voltage. So, this is the voltage when the current through the system is essentially 0, is equal to kT over E ln of IPH by IS naught, where IS naught is your reverse saturation current. So, this depends upon the material of the solar cell and also the kind of dopants, the concentration of the dopants, the width of the depletion regions and so on. So, we have simple expressions that relate both ISC and VOC. So, the short circuit current and the open circuit voltage to your incident photon radiation. So, when you change the radiation intensity, you can basically calculate the change in these values. So, now the new value of IPH is doubled. So, it is 2. So, let me write this as IPH prime, which is 2 times the original value, 1000 watts per meter square. So, the new short circuit current, so ISC new. So, I am going to write it as ISC prime divided by the original ISC, it is nothing but IPH prime by IPH, which is equal to 2. Therefore, the new short circuit current is essentially the double of the original short circuit current. So, this is nothing but 300 milliamperes. Similarly, I can write the value of VOC. So, VOC prime by VOC, again you are taking the ratio of these two quantities kT over E ln of IPH prime by IS naught IPH by IS naught. So, KT over E will essentially cancel. This we can simplify because the values of IPH prime, IPH are known. IS naught is not known, but we can calculate IS naught by knowing the open circuit voltage when the current intensity is 500 watts per meter square. So, from this we can calculate the value of VOC. So, VOC prime is essentially 0.55 volts. So, we now have a situation where instead of doubling the photon intensity, we are reducing it by half. So, IPH is nothing but 250 watts per meter square. So, we have reduced it by half. So, the new short circuit current ISC double prime will also be half. So, this will be 75 milliamps and the new VOC. So, let me write this as double prime is 0.48 volts. So, this we can get by following the same procedure, where instead of having it as 1000 we now have it as 250. Let me now go to problem 4. Problem 4 is also related to a solar cell. So, we have a solar cell of area A is given, and is connected to drive a load R of 20 ohms. So, R is essentially 20 ohms. So, we can actually draw how the solar cell connection looks. So, this is given as part of the question. So, you have the solar cell essentially connected to a resistor. So, R is the resistor. So, light falls on the solar cell. So, you have some light I which drives a current I. So, this in turn generates a voltage V that opposes the inbuilt voltage in the solar cell. So, the intensity of the light is given. So, that is 1 kilowatt per meter square. And we want to calculate the voltage in the circuit when the intensity is 1 kilowatt per meter square. The corresponding value of current for that is given. So, in the question, along with how the solar cell is connected, we are also given its IV characteristics. So, let me plot this. This IV characteristic is for 500 watts per meter square. So, we have current I, that is in milliamps, and we have voltage V. So, this is 0, you have 10, you have 20, this is 0.2, you have 0.4. Let me just extend this a bit, and you have 0.6. So, the IV characteristics So, this is the IV characteristics of the solar cell. So, this is drawn when the illumination is 500 watts per meter square. So, we are asked to calculate the current for a particular voltage or the voltage for a particular current when the illumination is now changed to 1000 watts per meter square. So, we can go to the problem. So, let us go to part A. So, when a solar cell is essentially driving an external resistor R, there is some current that is flowing through. So, this current at 500 watts per meter square illumination, I am going to call this as I 500. So, I 500 is given by the intensity of the light plus a voltage due to the potential barrier that is created by the resistor. This is given as I naught exponential EV over kT minus 1. So, this is a general expression that relates the current at a particular intensity to both the open circuit current, the short circuit current, and also the voltage when you have some external load R sitting on the system. So, from the graph we can essentially mark the values of these various points. So, when V is equal to 0, this is your short circuit voltage, the corresponding current I is minus 16.2 milliamps. This is nothing but I 500 comma pH, and just for simplicity I will write this as IPH. So, this is the short circuit current. You can also calculate or you can also look at the open circuit voltage, so that when the current is 0, the voltage is exactly 0.49 volts. This is the open circuit voltage. The question also says that the device at 500 milliamps or 500 watts per meter square illumination is essentially operating at point P. And for this we can calculate the current and the voltage. So, V is 0.45 volts and the corresponding current I is minus 13.1 milliamps. So, this represents the operating point for the circuit. So, we now have to use these to calculate the values when your solar cell is illuminated with 1 kilowatt per meter square. So, once again let me write the expression. So, I is equal to minus IPH plus I naught exponential EV over kT minus 1. So, I naught we do not know, but IPH we know. So, when voltage V is equal to VOC, which implies current is equal to 0, this is minus IPH plus I naught exponential E VOC over KT minus 1. So, in this IPH is known, VOC is known, the only unknown is essentially I naught. So, we can make the substitutions, and I naught is calculated to be 2.58 times 10 to the minus 11 amperes. So, this represents the reverse saturation current in the system. So, now the new illumination I nu. So, let me call it IPH nu. So, new illumination is 1000 watts per meter square. So, in the previous problem we saw that when the illumination is doubled, the short circuit current is essentially doubled. So, IPH nu is 2 times IPH at 500. So, this is minus 32.4 milliamps. So, the corresponding current is also given. So, I of 1000 is nothing but IPH nu plus I naught exponential EV over KT minus 1. So, this current is given and this is equal to 0.024 amperes. So, IPH nu we have just calculated, I naught is something we calculated from the data for 500 watts per meter square. So, this is known, this is known, the only unknown is the new operating voltage. So, we can make the substitutions so that the new voltage V nu is equal to 0.475 volts. We can also calculate the power in the system. So, power is nothing but V prime times the current. So, the current is I 1000, this is equal to 0.011 watts. We are also asked to calculate the efficiency of the system. So, the input radiation is 1000 watts. So, P in is 1000 watts per meter square and the area of the solar cell is 1 centimeter square. So, that is 10 to the minus 4 meter square. So, this gives you 0.1 watt. So, 0.1 watt is the input power, the output power in the form of electrical current is 0.011 watt. So, the efficiency in terms of percentage is 0.011 divided by 0.1 times 100, that is equal to 11%. So, let us now go to part B. So, in part B we are asked to calculate the load. So, to have a maximum power transfer from the solar cell to the load. So, once again the illumination I is 1 kilowatt per meter square or 1000 watts per meter square. So, in problem A we essentially looked at the load for a given value of current and voltage. We now have to find out the load at which the power transfer is essentially maximum. So, power P is nothing but I times V, which can be written as V times minus I of 1000. So, we have I 1000 plus I naught exponential EV over KT minus 1. So, this is the expression for the power. If you look at it, everything here is a constant except for the voltage. So, to have maximum power, so at maximum power dP over dV must be essentially 0. So, we can differentiate this expression for P. So, dP over dV, and that is given by I naught KT by E V times exponential EV over KT minus I 1000 plus I naught exponential EV over KT minus 1, this is equal to 0. So, this you can get by essentially treating this as the differential of two functions. So, you differentiate one keeping the other constant, and then you differentiate the other keeping the first one constant. This is now equated to 0 for maximum power. So, in this case I naught is known, I 1000 is known, this is the short circuit current at 1000, which is 2 times the short circuit at 500, and we just calculated it. So, the only unknown is essentially the voltage. So, if you solve this, this gives the voltage Vm, which is the voltage at maximum power, and this is equal to 0.436 volts. The corresponding current Im is 0.031 milliamps, and the resistor R is Vm over Im, which is 14.07. So, this is essentially the load at which the power is maximum. We can also do this for the illumination at 500 watts per meter square. So, if I is 500 watts per meter square, we can repeat this. I will just write the answer. Im is 0.015 amps, Vm is 0.42 volts, and the load Rm is essentially 28 ohms. So, the last part of the question, part C. So, we need to connect solar cells in order to drive a calculator. The calculator is to be used at a light intensity of 500 watts per meter square. So, when we have solar cells each having a particular voltage, and they should essentially be connected in order to give the voltage of 3 volts, these solar cells should be connected in series. So, the solar cells should be connected in series. So, if you look at the initial operating condition that was specified in part A, the voltage for each solar cell is 0.48 volts. So, voltage per cell is 0.48 volts. We basically want a total voltage of 3 volts. So, the number of cells is essentially 3 divided by 0.48 and you round off to the highest integer. So, this gives you 7. So, we need 7 solar cells all connected in series to basically supply enough voltage to run a calculator. Let us now go to the last problem. So, problem 5 is related to a photoconductor. So, we saw some variation of this problem in the previous assignment, assignment 7. So, you have a photoconductor that is placed under uniform illumination. It says the absorption of light basically causes an increase in current. The increase is given when you have a particular voltage, then the radiation is cut off, so that the excess carriers start to recombine, and when that happens the carrier concentration drops and the current also drops. So, in this particular case we are going to take electrons to be the minority carriers. So, the increase in current is always due to the increase in the minority carriers. This is especially true when we have weak illumination, where we assume that the illumination intensity is smaller compared to the concentration of the majority carriers. So, electrons are the minority carriers and we have also given the electron mobility. So, mu e to be 3600 centimeter square per volt per second. So, the first part of the question, we need to calculate the equilibrium density of the electron hole pairs generated under radiation. So, we can write an expression for that. So, the current I, which is your photocurrent, is due to the excess electrons that are created. So, this is equal to delta n, which is the excess electrons, times the mobility times the electric charge E of the electron times an electric field E that is applied across the material, and since it is the current we have to multiply by the area. So, this expression is got from the original expression for conductivity. Conductivity is Ne mu E plus Pe mu H. Conductivity sigma is related to the resistivity as 1 over rho, and R is nothing but rho L over A. So, this is 1 over sigma L over A. So, this is the expression for the current due to the increase in the electron concentration. In this particular case IP is given. So, this value is 2.83 milliamps. The electron mobility is given. So, this should actually be mu E. So, electron mobility is given, the dimensions of the device are given, E is the electric field, this is nothing but the voltage V divided by the length L. So, the only unknown in this expression is delta n. So, delta n is 1.47 times 10 to the 13 per centimeter cube. So, this is the excess electron hole pair concentration that is created when light is shining. Part B, we want to calculate the minority carrier lifetime. So, when the light is switched off, the concentration of the minority carriers essentially decrease, and this is given by the value at a particular time t divided by the minority carrier lifetime tau. So, since we are dealing with electrons, I will call this tau e. So, you can write this in terms of current, and if you do this, dIp over dt is nothing but E mu E V over L times WD d delta n over dt. d delta n over dt is nothing but delta n at time 0 divided by tau e. So, delta n at time 0 is nothing but what we calculated in part A, dIp over dt, which is the rate at which the current falls, is given in the question. This value is 23.6 ampere per second. So, this is known, the only unknown is tau e. So, tau e is essentially 119.6 microseconds. Part C, we want to calculate the excess density of electrons in holes 1 millisecond after the radiation is turned off. So, part C, we want to calculate delta n 1 millisecond later. So, delta n at time t is nothing but delta n at time t equal to 0 exponential minus t over tau. So, t is 1 millisecond, delta n at time t equal to 0 is what we calculated in part A, which is the excess equilibrium concentration. Tau is what we calculated in part B. So, delta n is nothing but 3.44 times 10 to the 9 centimeter cube. Once again, we are assuming a condition of weak illumination, so that any change in conductivity is driven by the minority carriers. So, that in this particular case, the change in concentration of the majority carriers, which are holes, is not significant enough to affect the conductivity.